Alright guys, so this first video is the proof for the following derivative rule that we learned a while back, the power rule. The derivative rule that we learned a while back is the derivative of x to the nth power is equal to n times x to the n minus 1 power. Alright, you guys ought to be patient when school's not in session. When I try to record these videos, the computer has a major lag issue, so there's going to be a lot of times where we just have to kind of wait for the computer to catch up with us. Okay, so before we begin that proof, I'm going to need to give you guys a little bit of some background here. This background is not part of the proof. You do not have to include it in your proof. I would like to see you include it in your notes that you're taking for the extra credit. However, it doesn't need to be in the demonstration of the proof whenever you take your test if you choose to do that extra credit option. So, first of all, before we begin, let's consider this fact. A plus b to the 0 power. You guys know that that is 1, hopefully. There's some lag, so we'll have to wait for the computer sometimes here. All right, now another situation. Suppose I have a plus b to the first power. What is that equal? That is equal to a plus b, right? Anything with the first power is just itself. Now I'm going to do something a little bit weird here, but I want you guys to be aware of the coefficients there. The coefficients there are 1 and 1. All right? Next, we're going to do this. Now you guys know this from one of our lessons last week, that a plus b to the second power. I gave you guys a shortcut for that. It is the following: a squared plus, now there's a 2 in the middle here, but I'm going to skip that for now because I want it to be red. And there's some of that lag I was telling you about. Trying to go slow so the computer can keep up with me here. You guys can put the YouTube video on fast when you watch it though, and that way you guys can kind of speed through this a little bit quicker if you want to. But once again, I'm going to put the coefficients there in red. Now, one that I wanted to get to, but I didn't, and it really wasn't that big of a deal, but is the following one here. If we do it to the third power, now the shortcut for that would look like the following. The coefficient's going to be 1 for the first term. The second term is going to have a coefficient of 3. The third term is going to have a coefficient of 3. And the fourth term is going to have a coefficient of 1. The a is going to be a cubed, and there will be no b term there. However, what happens is that every term after that, the a goes down by 1 power. So now it's going to be a squared. There's some of that lag. Let's wait for it. Okay. A squared. The next one's going to be a to the first power. And the last one won't have an a at all. You can think of that as a to the 0 power. The b's do the same thing. It's just they go backwards. So over here, this is going to be b cubed. This one's going to be b squared. This one's going to be b to the first. And as I mentioned before, there won't be a b on the first term. So after doing so many of these, now you could definitely have FOILed this out and expanded it the old school way. It would have taken you a while. But the point is, I just showed you guys there's a pattern here. The pattern is really obvious for the powers, right? Whatever term comes first, the power starts at this power over here. So a starts at a power of 3, and then it goes down by 1 each time. until it's gone. And then the B does the same thing, but it starts on the right side and works its way up. But what's not an easy pattern to see is what I've highlighted in red here, the coefficients. Now, the coefficients follow a pretty interesting pattern. What I'm trying to do is I'm trying to show you guys that there's essentially a rule that we can use, a pattern that we can observe for finding a plus b to any power that we want. Okay? Well, as I've already mentioned, we already know that, you know, a is basically going to start at n, and after that it's going to go down by 1 power each time. B does the same thing on the other end, and it's just going to go up 1 each time. You can also notice that there's a difference in the number of terms. Up here there's only 1 term, then there's 2 terms, and there's 3 terms, and then there's 4 terms. So we have this definite pattern going on. And so now what I want you guys to be aware of is what rule can we use to figure out what a plus b to any power is. So we're going to try to figure out a pattern, and then we're going to use that pattern to see if we can do a plus b to the 4th, and then I'll let you guys see if you can do a plus b to the 5th. And remember, all I'm doing right now is I'm giving you some background that you're going to need in order to do the proof, which is what we're really trying to work on right now. Remember, our goal is to do this, right? But I have to give you this background before you guys will be able to do it, and you'll see why once we start the proof. Okay, some of you might have seen this stuff in your pre-cal class, some of you might not have. But here's what I'm going to do. I'm going to go ahead and I'm going to erase all the green stuff right now. And I want to just really focus on those red numbers, those coefficients. Okay, so let's focus on those for a minute. First of all, you'll notice that every row always starts off with a 1 and ends with a 1. Okay, the issue is going to be these middle numbers here. How am I going to get 2? How am I going to know what that is? You know, so I already know that for this a to the 4th power, I already know a couple of things. First of all, I know that the first term is going to have a 1. I know that the last term is going to have a coefficient of 1 as well. The problem is, I know there's going to be 3 other numbers because there's 1, 2, 3, 4. There's got to be 5 here. So I need a number here, I need a number here, and I need a number here. And it just so happens that there's kind of an interesting pattern here. And this shape is what is known as Pascal's triangle. You guys can see it's kind of making a triangular shape. And right now I'm going to show you guys how you can figure out what those numbers are. There is a pattern. Here's the pattern. 1 plus 1 is 2. Right? If I take these two numbers and add them together, it makes 2. Same thing here. 1 added with 2 makes 3. 2 added with 1 makes 3. So now we have a neat little way to figure out what the rest of these are. So 1 and 3 make 4. 3 and 3 make 6. And then finally 3 and 1 make 4. Now I'm not proving that this is true to you. I'm just using something known as inductive reasoning. I'm looking at a pattern. I'm just continuing the pattern. Is this really what it is? Well, it turns out it is. And that pattern will hold indefinitely. And so that's kind of the trick. But I think something a little bit more interesting here, and the only thing we really need to know about is the following, is that first of all, it always starts off with 1, and the next number is always going to be whatever power you started off with. So here the power is 4, that's what the second number is. Here the power is 3, that's what the second number is. So on, right? It just continues all the way through. So those are some good patterns to be aware of. So now knowing that, let's see if we can continue figuring out the rest of this really quick. I've got some lag I'm dealing with here, just a moment. Okay, so I've got my coefficients. Let's finish doing a plus b to the fourth power. So we know that this one's going to be a to the what? Fourth power. And then it's going to be a to the third, a squared, a to the first, and then no a at all. B does the same thing, but starting on this end, it's going to be b to the fourth, b to the third, b squared, b, and no b at all. And that's what you would get if you expanded this. So I'm dragging this out a lot, but now we kind of have a nice little shortcut so that we don't have to FOIL out this huge thing. So check it out. I can very easily now find what, for example, let's say a to the fifth is. If you guys wanted to, you don't have to, but if you wanted to, you could pause the video here and see if you could figure out what a plus b to the fifth power would be. So we know that the first number is going to be 1, and then 1 and 4 make 5, 4 and 6 make 10, 6 and 4 make 10, 4 and 1 make 5, and then we close it off with a 1. Then we have to put the variables in. It's going to be a to the fifth, a to the fourth, a to the third, a squared, a and no a, and then b to the fifth, b to the fourth, b to the third, b squared, and b. So there you have it. Of course, all these are being added together. So this is going to be something that we're going to need to do our proof. But there are two big takeaways that I want you guys to be aware of here. Let me scroll down here. Maybe I'll make a list of our takeaways here. And in fact, I'm going to say that there's 3 takeaways. Takeaways for this background for our proof. Here we go. First of all, the first term, got some lag. The first term, like this one for instance, it's always going to be just a to the nth. In other words, whatever this is, the first number, to that power. That's always going to be your first term. Okay? Now your second term is the other thing that we want to pay attention to. That's something else that's going to be helpful to know about for our proof. The second term, the coefficient is that power. So it's going to have, if you have, I guess we're just going to write this really quick. For a plus b to the nth power, the first term will be a to the nth. The second term is going to have a coefficient that's equal to the power. So in this case, my power is n, so the coefficient will be n. And then it's going to be a to a power that is 1 less than the original power. So my original power here is n, so 1 less than that would be n minus 1. And there will also be a b term after that to the first power. So there's our 2 big takeaways here. Is the first term is a to the nth. The second term is n times a to the n minus 1 multiplied with that second term, which is a b. And it's very important that this is b to the first power. So I'm going to highlight that. That means something. Now, I don't care about the third, fourth, fifth term, actually. For our proof, those things are not going to be necessary to be aware of. Okay? But I think that, I said 3, but I think this kind of wraps it up here. This is what's really going to be helpful. I guess I'll go ahead and put 3. I'm not making up my mind here, am I? The last term, got some lag, just a moment. Okay, the last term is always going to be b to the nth power. Okay? So, there you have it. We know our first term, our second term, our last term. We have a bunch of other terms in the middle that we don't really care about for our proof, but there it is, okay? So that's the background that you're going to need for our proof. So now that we have the background established, let's go ahead and do the proof for the power rule, okay? So I want to prove, once again, I want to prove, got some lag, that the derivative with respect to x of x to the nth power is n times x to the n minus 1. Now you guys might notice that looks a little familiar. That was part of our takeaways from our background for this proof. Okay, so let's go ahead and do this. So I'm going to say that let's have a function here, f of x is equal to x to the nth power, and I want to prove that f prime is equal to this over here. All right, so first of all, we're going to use that limit definition, right? So f prime of x, got that lag again, f prime of x is equal to the limit of delta x, as delta x approaches 0, of our difference quotient. Once again, sorry I got to go so slow, guys. The computer just has a major lag when school's not in session. Actually, I'm going to change how I write this. So our first term, as you guys know, is x plus delta x, right? So if I have x to the nth power, then what it's going to be is x plus delta x to the power of n. Now, if you think of x and delta x as a and b, you can kind of see why we were doing that Pascal's triangle thing a little while back. All right. So there's our limit definition of a derivative of a power function, right? And so now I want to prove that it equals n times x to the n minus 1. How in the heck are we going to do that? Well, we're going to use the fact that we just explored on the last slide. And here's what we explored. Got some lag. There we go. Once again, if you guys don't want this video to go slow, usually YouTube has some controls where you can speed up the video, make it go a little bit faster. Unfortunately, I am stuck at a snail's pace with our software here. All right. Well, here's what I'm going to do, is I'm going to use the rule that we just talked about on the last slide to expand this out. Now, I know that my first term, if I were to actually do this to the nth power, my first term is going to be x to the nth power, right? That was one of our takeaways. The next one is going to be have a coefficient of n, and then it's going to be x to the n minus 1 power. And then we are going to have 1 delta x here after that. Just like, remember, this is kind of like our a, and this is like our b in this case. And then we have a whole bunch of other terms after that. And the last term is going to be delta x to the nth power. And then we still have our minus x to the n, which is this part over here. All right. And then we have our delta x on the bottom. All right. So, first of all, x to the n is going to subtract with x to the n, and those two things are going to cancel each other out. Now, what's significant on our next move here is that every term up here will have a delta x in it now. It starts with delta x to the first power, then it goes to delta x to the second, and third, and fourth, and so on, until we get to delta x to the nth power. And so what happens is this delta x is going to cancel one delta x out of every term that would be on the top. So here, it cancels out that delta x completely, and so that delta x is gone. And it will cancel out a whole bunch of other delta x's in the middle here that I didn't write. It will also take away one of these delta x's at the very end, so we're left with delta x to the n minus 1. Okay? But the point is every term that's left after this one will still have at least one delta x present. So let's go ahead and write what we have as a result of this. The limit as delta x approaches 0 of the following. Now we have n x n minus 1. Got some lag, just a moment. Now we got some unwanted writing going on. Darn it. It's still doing it. Oh, technology. All right. And then after that, we have a whole bunch of other terms. We got also some major lag going on right now. Nice. It's drawing when I don't want it to. Very good. Okay. And then every one of those terms has a delta x in it. And our last term is delta x to the n minus 1. It used to be n, but we canceled the 1 out of every term, and so now this one has 1 less, right? And this is what I'm left with. Well, now, if I do my direct substitution, and I plug in 0 for every delta x, then every term is going to just cancel out, including the last one, because you're plugging in 0. And all that you're left with after that is the answer, which is n x n minus 1. And there's our proof. So I just showed, using what we know about binomial expansions, to prove that the derivative of a power function is that power in the front, and the power decreases by 1. And that's why we can do things like, you know, finding out that if you have f of x equals x to the 5th power, we know that the derivative is basically going to just be the second term in that sequence of an expansion. So, and we know that the second term is always going to be whatever power that is times x, and the power after in the second term is always 1 less. And so that's the power rule that we learned a while back. Okay? So that's your first proof. This slide here is the slide that you guys would need to be able to recreate on a proof in order to receive credit for it on our next test. The stuff in green there is not required. I'll just assume that you know that those things are canceling out, but all the black stuff there is something that I would expect to see. Okay? So that's our first proof.